Okay. All right. So I'm not going to tell you what the answers are because these are your homework problems, but I will give you a category of hint, which is for this problem, it is of this form for, I think, pretty much every single one of these problems. And so you just have to figure out what's A and what's B. Is it the number of consonants and number of vowels? Something like that. Particularly this one, this is the combination of begin plus end minus begin and end, right? Because we don't want to, so this, I believe, is secretly an exclusive or, where we want to either begin or we want to end, but not both. That's too much. And so we overcount that if we just add, here's all the possibilities where we start with a vowel. Here's all the possibilities where we end with a vowel. And then you just subtract the overcounting. And so B, C, and D, or if you can solve A, then B, C, and D is just variations. For 2 and 3, they're pretty much the same problem. I encourage you to look at derangements, which is an equation that we looked at last time. Any questions before we move on? Great. Let's talk about the pigeonhole principle. So, in a unique twist of fate, most of my problems end up being combinatorial, where I've had my AV dilemma. I've also had a soccer dilemma where I asked 6 people, hey, do you want to go to a soccer game? And there ended up only being 5 spots in my car. And so the problem is that all 6 people who want to go to the soccer game cannot fit in my car. This is an example of something called the pigeonhole principle. Um, and the idea is, so these are a box of pigeonholes. So like it's like a grid, and each pigeon gets to roost in its own hole. And so the issue comes where we have, if we have n, okay, hold on, let me say what the book says. If we have n pigeons and we have m pigeonholes and we have n greater than m, then so like in this example, we've got n pigeonholes, and then we've got one who wants to find a place to roost, but all of them are filled. And so it's going to have to roost with one other bird. So like at least one pigeonhole has more than one pigeons. Make sense? So at least one pigeonhole has more than one pigeon. And so we can write this in theorem form. This is theorem 11.4, where it says, let A be a finite set. And we're going to partition A into subsets. So partitioned into subsets, and we'll just say that they are called S1, S2, and so on up to SM. Right? So we've got this big long set and we've chopped it up into subsets, and there are M of those subsets. Then, if the number of things in A is N, and N is greater than M, then at least one of these subsets contains more than one element. Right? And this seems fairly straightforward. Like, if I have 5 spots in my car and I have 6 people who want to go, then not everybody's going to fit in my car. Then maybe one person has to like share a seat with someone else. If we have 5 people to do a 2-person job, then like we've got to squeeze someone else in there too, right? So this concept is easy to grasp, and so we're going to use it to solve some interesting problems. So first of all, let's assume that we're at a Ohio State football game, and we're making the conjecture that there are at least 2 people at this game who have the same 2 initials, first and last, and they were born in the same year. Which seems crazy, right? Like, there's a lot of people who would go to this game, and like first and last and year seems like way too much of a coincidence. But we can show this mathematically. So how many ways? So we're looking for a sequence of like first initial, last initial, the year they were born. And how many options do I have for people to have the same first initial? 26, right. How many options do I have for people to have the same last initial? Right. How many options do I have for people to be born in the same year? Yeah, so something like 100. I mean, you could go up to like 110 or something if you like look up the oldest person in the world. I think 100 is a good guess for people who would actually be going to football games. Um, and so what do we do with these 3 numbers? Multiply them. Why not add? Right. So we're trying to come up with like this exact sequence matches, right? First name, first initial matches, last initial matches, year matches. And so we're trying to come up with a sequence of these 3 things have to match. Okay. 26 times 26 times 100. Would someone with a calculator? Okay, 67,600. Um, okay, that's a big number. We're at an Ohio State football game. Would someone please Google what's the capacity of Ohio State's football stadium? One hundred two thousand. This is the pigeonhole principle because we've computed here are all the possibilities for like someone to have the same first last initial and be born in the same year. but there's 102,000 people who are going to go to this game. And so this is the pigeonhole principle in action. Because there's less of these possibilities than there are people who are going to the game. Therefore, by the pigeonhole principle, there must be at least two people who have the same two initials and were born in the same year. Do you remember on the first day we talked about like how many people in San Francisco like have the same amount of hairs on their head? This is the pigeonhole principle. All right, so we've got if 7 distinct integers are selected from the set 12 in square brackets, which is 1, 2, and so on up till 12, then 2 of the 7 must have the unlucky sum of 13. Talk with your neighbor for a second. How do you think you would figure this out? Okay, so yes, that approach is correct. So, right. So we're thinking of like, we've got 7, we've got 12. And so the approach for these kind of problems is less, so like it uses our combinatorics and counting skills, but it's more so on the proof side of things, where how can we can come up with a solution, but we need to explain why this thing holds. So this is why we talk about proofs before we do this. So we've got 7, we've got 2, we've got 12. And then you're arguing that we have 6, as these are the numbers that we care about in this problem. So 12 is all of the possible numbers that we care about. 2 are the ones who have to add to 13. 7 are the number of things we're drawing. And then 6 is half of 12. So yeah, so the question here is, what are the pigeons and what are the pigeonholes? See, and this is why math is fun. They never told you in high school that you get to talk about pigeons and pigeonholes. All right, so in this, hold on, you tell me, what are the pigeons? Which number corresponds to the pigeons? We've got to vote for 7. We've got 7 and vote for 12. Votes for anything else? Okay. Between 7 and 12, who votes? So 7 versus 12. Who votes that 7 is the number of pigeons? 1, 2, 3, 4, 5, 6, 7. Okay, why 7 as opposed to 12? Yeah,
Because you're only choosing 7 of the numbers out of the set of 12.
right. So 7 is actually our number of pigeons. And so then for the pigeonholes, that's the strategy where we have what? 1 and 12 are 13, 2 and 11 is 13, 3 and 10 are 13, 4 and 9, 5 and 8, 6 and 7. And then if we go one more, it would be 7 and 6, 5 and 8. So it's just the same. So addition is commutative, so we don't care about the order of those. So these end up being our pigeonholes. Because if we're picking, so I've got 12 numbers in a hat and I'm picking 7 of them. So I've picked at least 6. And I've picked one more than 6. So that means that even if in the worst case I pick all of the ones, like if I pick 1, 2, 3, 4, 5, 6, I've picked another one. I picked a 7th number, which means in the worst case, if I pick 7, then oh, I've picked 6 and 7. So it falls into that pigeonhole. If I pick all of 7 to 12, none of those are all too big to add to sum to 13. But since I pick 7 numbers, if I pick 1, then that will add with 12 to 13. If I had picked 3, that would sum with 10 to 13. Right? So since I'm picking one more than half, that guarantees that I will fall into one of these categories. So the pigeonholes are these, the sum total of which is 6, because there are 6 of these pairs that sum to 13. Questions on that? Confusions? All right. So let's assume I have a very big table and I have invited 90 people to this meeting. And I'm seating them equally spaced at this very large table. And of the people who I've invited, more than half of them are women. I want to prove that there are 2 women who are seated diametrically opposite to one another. Side note, when I was preparing this problem, I read this and then my Hamilton brain is like diametrically opposed foes. That's not related. Right, we could make this into when you make up your own question, you could make it into a Hamilton question. But I would like to prove that there are 2 women who are seated opposite to each other. How do I do that? Talk about it.
Yeah.
Okay. Convince me. Give me an explanation, if you would like.
Well, we were saying this like the last one where so half of 90 people is 45. So if you had like all of the women on one side or like every other one, they're you have more than half are women, so there has to be at least one on the other side. And that woman is going to be diametrically opposed to them.
Yeah. That's the idea. So yeah, so a good strategy is to break it in half. And if we have like more than half as somewhere in the problem, then there we go. All right. I heard an interesting variation on the problem. What was it of like if we sit, what was it like a woman and man next to each other?
Like sit them alternating, like starting with a woman, with a pattern, and then a woman or a man, or like two women, and what would it like end in?
Yeah, I think that's an interesting question. It's slightly different than the pigeonhole principle, but um still an interesting combinatorial question. And so yeah, so the advice I gave is to think about this like not recursion, um induction, which kind of recursion like, where instead of starting with 90, that seems difficult and hard to figure out. But if you start with 2, a very small table, and then up to 3, and see if you can generalize based on that. All right, so I have activities for you today for the last 20 minutes of class. What I would like for you to do is I would like you to come up with your own problem and solve it if you can. But once you do that, please come tell me what it is and I will write it down and we'll present it to the class on Wednesday of here are some interesting problems. Yeah. Make sure it's unsolvable. I mean, I feel like you would have to work really hard to come up with a problem that is unsolvable. You might get a PhD if you come up with an unsolvable combinatorics problem. All right, so I will pause. Do we want to do same groups or random groups? This is not a great question to ask you guys. Let's do same groups. All right, go for it.